My name's Dave Pradden, and my PhD supervisor, Luke Matheson, and I recently had a paper accepted at the Australasian Database Conference 2023, which just concluded in Melbourne. In this paper, we present some early results and make the claim that this area is worth more study. As I go through the paper, we're going to look at two kinds of relations, but let's begin with the familiar data relation. Our relational model is based on relations, and I'm going to start out by introducing some of the basic assumptions that we don't even hardly ever think about. The reason I'm calling these out at this moment is because later on in our presentation, we're going to abandon all of these assumptions and replace them with different ones. But let's run through this. So we assume that the predicate, the truth value that is true for every row of the table, is expressed in natural language. So for example, a table might have a predicate as cars registered in New South Wales, and the table name might be NSW cars. We assume that our lists start empty with just a schema. We assume that they're of finite extent, and we, in the most cases, our tables are mutating, where we're using data manipulation language, inserts, updates, and deletes to give values and to update them. The queries, relational queries, we're going to use SQL in this presentation, range over the rows that actually exist. And because we're capturing information from the real world, we have obligations for confidentiality and integrity. At the same time, when we express our relational expressions in SQL, we're familiar with them being treated as expressions, which get evaluated over relations. And then we have the sigma, meaning a selection, or the pi, or the projection operator, and then joins over those groups of tables. Well, going back to the origins of the relational model, Codd in 1970 introduced a new way of organizing data. Previously, it had been organized as a network or a tree, and the obligation of the programmer had been to provide a procedural access path to that data. And so the great benefit there is that we can now, using an expression like the one on the right, we can just say what we want at a higher level, and the database will go and figure out the best access path. Now, the second benefit that we've gained from this is, I would call that data reusability. So we capture data in a database, we have a high degree of confidence that whatever we want to know in the future, we can structure a query around that and get the information that we want. We don't have to go back and reorganize our data. So data reusability. Now, two great benefits: data independence, data reusability. But there are three benefits from the relational model that have to do with computation that I don't think we're yet reaching. The first of those is got to do with program ergonomics. So here we have the happy programmer working in SQL, in this case, in a declarative mode, expressing what they need to how they need to transform their data. Then in another part of the application that they're building, they need to encode some business rules. Maybe they're regulations, maybe they're laws, maybe they're corporate policy, and finds that they aren't able to express that using relational algebra in a language like SQL. And so they turn to a stored procedure, or they have to use it in the host language, and within which the SQL expressions become embedded. I think there's an opportunity here for us to stay within this declarative environment for capturing our business rules as well as our data transformation. The second issue that's not yet been, second opportunity that's not been taken through the relational model is reusability of code. So to show this point about reusability, I'm going to introduce the running example that will be used through this presentation of a GST calculator, or if you're from the UK, a VAT calculator. This little calculator is on the web at that address there. And here's how it works. So you can put in the amount of the transaction without the GST, and inside the application, there's a little function that takes that amount and will generate the price and the GST amount from that. Alternatively, you could enter in the price that the user pays. And there's a second function that will calculate the GST amount, ex-GST amount, and then the actual amount of the GST or VAT tax. There's a third way that it operates, and that is that you could enter in the amount that you paid as tax, and it will calculate the other two ways. Now, you'll notice that there are three different functions involved here that are mapping three different values to two other values. And so this is implemented in a way that you have to replicate this business rule 3 times. Wouldn't it be nice if we could have this created as a relation? So we'll just capture the business rule once, and then we'll query that relation for the 3 different use cases without having to repeat ourselves. So that's the second value that has not yet been achieved from the relational model. The third is efficiency. So the 3 papers that you'll see on the screen there, they are all about replacing stored procedures with relational algebraic expressions. Well, why? Why would there be research going on about how you replace stored procedures? Well, it's because of efficiency. So stored procedures are opaque. The query optimizer is unable to examine them. They're unable to reorganize them, unable to move the predicates around. And so this becomes a performance block in real workloads. And so what I'm suggesting is that there are a way through using relations for computation that will minimize the scenarios where we would need to leave relational algebra and to go across the boundary into a procedural world. So there's 3. Here's the outline of this presentation. Firstly, we'll have a bit of a look at a worked example and go through the definitions and explain how we can use relational expressions for computation. We'll then have a look at an evaluation that we conducted. We'll look at related work. And finally, we will look at some implementation issues and next steps. Okay, so into the worked example. If we return back to our running example, we've got our calculator and we have an intention of expressing the Australian GST relation as a relation in a database. Now, if we did that, we could then have a select statement. The select statement would go something like select star from Australian GST, where, well, depends what we know. We could plug in the price, we could plug in the price without GST, or we could plug in the GST amount, and the response from this query would be a single tuple relation shown there, and it would be the same in every case. Now, that's unremarkable. It's a good use of SQL. It shows how the data in that table is reusable. But how shall we implement this? And here's a question. How many rows are there in this table, Australian GST? If you're not sure, you can pause the video at this place, have a bit of a think about it. But the answer is, of course, that this table contains infinite rows. How many prices are there? How many float values are there as price? There's quite a few. So to explain how this might be possible to include in our database, even though it has infinite rows, I'd like to introduce a different kind of relation. Just as much a relation as a data relation, I'd like to introduce to you a sigma complete relation. And this is where we're going to see these parallels with the assumptions that are just a part of our everyday expectation of databases, that we're going to break those assumptions, and I'm going to show you how it could work out. So the first one has got to do with the predicate of this relation. In a sigma complete relation, the predicate is actually a Boolean expression. So it is in relational algebraic terms, it's a select, a sigma, or in SQL terms, it's a where clause. And here is the business logic of the GST expressed as such a Boolean expression. X GST amount equals price minus GST amount. Makes sense? And GST amount equals price on 11. Now, it's important to note that these are Boolean predicates. They are not assignment statements. Now, this is the first difference. The second difference is that sigma complete relations start full. They start complete. They are complete relations, and they are shaped by the predicate. In terms of the extent of sigma complete relations, they are either finite or infinite. They're not mutating, they're constants. They also, when we run a query over a sigma complete relation, the query ranges over all possible rows in this relation. And this relation contains no information about real world entities. All it contains is a capturing of a business rule or logic between entities represented. So just to back up and explain why these things might be called sigma complete relations, the reason is because they start complete and then they are shaped by a relational sigma select. So let's go back to our example and press on. So if we had an intention of using a sigma complete relation, we'd need to have some kind of textual form to capture our GST relation. And we're going to use this language there, complete price as a float, XGST amount as a float, and GST amount as a float. Now, the meaning of that form can be shown quite clearly through relational algebra. It's the cross product of three float values. Now, depending on how your imagination works, you may wish to consider that as a three-dimensional space with each tuple in that relation representing a vector in that space, or you may prefer to think of it as a very long table that just goes on. It's just a table after table, row after row after row of values that goes on forever. Okay, so we've just seen how we could express the idea of a complete relation in an SQL-like form and what it means. Let's go back to our example and let's actually define this Australian GST relation in our database. So we're going to start out with this complete expression that I showed you on the previous page, which represents, and I'm showing it also in the expression form from the database optimizer, it's a cross product of three reals. And we then are going to shape that complete relation with this predicate. GST amount equals price on 11, and the XGST amount equals price minus GST amount. So this is the same as what we saw on the previous slide. And finally, we're going to enter it into our database as a view. So create view GST as. So now we have a sigma complete relation in our database as a view, and now we can use it to solve to drive the little example that we showed earlier. Okay, so now moving on to an example from running that website. Let's say we knew that the price was $110. How would the database optimizer actually give you the rest of the values? So we'll showing this query in the form that it would be viewed by the database optimizer. Australian GS, we're looking at a selection with price equal to 110 over the sigma complete relation. Now, in some world, not ours, we could get out our spyglasses and we could look down this infinite table and find the row where price happened to be 110. For us, that's not a winning option, so we have to do it, approach it in a slightly different way. And to do that, we're going to call on a very familiar friend, which is condition pushdown or predicate pushdown or predicate migration, which is a very familiar technique from database optimization, and we're going to apply it in this situation. Okay, so we took the sigma that was outside of the sigma complete relation and we pushed it inside. And now if you do that, you find that we have prices equals to 110, and we know already that the predicate gives us, there's another two lines. If we then plug in the $110 into these formulas and work it through, we find that GST amount is at 10 and XGST amount is 100. So that's very straightforward application of what is called predicate propagation, constraint propagation. and is very familiar to people from the constraint process programming world. So what we've seen there is that our database optimizer is able to directly provide the required value without doing any searching, even though in principle, the base relation is infinite. So having shown you that worked example where we've seen how you can define a sigma complete relation, how you can enter it into your database, how you can issue a query, and how the query optimizer can find the answer, I'm going to turn now to look at the evaluation that we conducted as part of the paper. So to evaluate sigma complete relations, we took a worked example, a use case that was done under the auspices of the Observatory of Public Sector Innovation in the EU, was conducted by Salsa Digital, an Australian cloud vendor, using a technology called OpenFisca, which is a Python, best-of-breed Python system for encoding business rules and logic, particularly with a lot of application in the area of law and regulations. So this pilot project looked at providing end users, ordinary punters, with the opportunity to have a question and answer session to discover were they up to date with their COVID-19 vaccinations, or did they need a COVID-19 vaccination in their workplaces? And each of these depended on about a half dozen different data points. So did the implementation, what was the result? Well, you can see on the right-hand side there some of the output from the work. We found that by asking key questions, it was able to give you the correct answer. It was also able to capture aspects that were determined in addition to what the information that was given, and also identify which values were underdetermined by answering the questions. The sigma complete relation implementation passed all 113 test cases for the pilot, and it also had a couple of benefits. Firstly, the query algorithm was able to choose question ordering based on prior answers to ask the minimum number of questions to give the result, whereas the original proof of concept had a fixed order of asking questions. And secondly, sigma complete, because of its relation, because of its interest in, or its ability in its reusability aspect, is just as easy, just as comfortable answering questions of, like, in Western Australia, which role requires 3 vaccinations, as it is answering the forward question is, well, do I need a vaccination given my role? In addition, when comparing the number of lines of code that are required in OpenFisca versus in a sigma complete relation, the code was about an order of magnitude less across those 2 examples. Now, my claim is not that this proves that sigma complete relations are the best thing since sliced bread, but rather that there's some interesting pointers there. There's more work is required. Okay, so having had a look at the evaluation, let's now turn to just surveying quickly some of related work. This related work goes back over 50 years. The basis, and I'll just point out on the slide here, just walk us around this slide. The foundation of this work is lambda calculus, the predicate calculus, and the relational model. And they are intrinsic and underpin all of the languages that are, I'm going to talk about all of the paradigms and languages that are on this slide. This tree captures a harmonious mutual accommodation of many different technologies that is perhaps my dream. It sort of captures something about what this work is pushing towards. And this relational tree, we could say, is got roots in data relations on the right-hand side, and it has roots in complete relations, or that is search spaces, mathematical search spaces on the left-hand side. So let's just start on the data relations side, and in no particular order, we have functional programming paradigms definitely related. Prolog, data log, and then SQL, the relational expression engines. PRQL and Malloy, amongst others, are more recent entrants into this space and are worth keeping an eye on. So if we go over to the constraint processing side, there is a wide variety of languages and paradigms that have explored this space. I'm not going to go through those in detail now, but just safe to say that if you are curious, there's a bunch of references on that slide there for you to follow up. Okay, so we've had a bit of a look at a quick survey of related work. It's extensive. I'd like to now turn to the area of implementation and of future work. So just straight off the bat, I'd like to make the observation that there are no existing implementations of database optimizers that are equally comfortable in dealing with data relations and dealing with sigma complete relations. That product does not exist. Where is the work in that? Well, one of the things that needs to be added to our current database optimizers to enable that is great fluency with predicates, moving them around the tree, evaluation tree, to make sure that the sigma complete relation, which is a search problem over this over the cross product space, has as many constraints as possible before the search commences. Because as you saw in the previous example, collecting those predicates may reduce the search space to zero, that the answer just falls out through the implication of all of the constraints. The second area that I'd like to highlight that is quite relevant is in the bottom case there, where we have, I'll just flip back to that so you can see that. We've got a join over two sigma complete relations. It's always the case that a join over two relations where they have common variables in common will lead to a stronger problem that's better solved together, which may again reduce the element of search and give the answer directly, because all the constraints come up with a unique or very low cardinality solution. So that's before me, and that's the challenge that my PhD studies have set me. And in conclusion, I'd like to sum up what I've presented this morning. First of all, we've seen how our programmers can stay within a single paradigm and improve programmer ergonomics, so that this business rule that's required can be expressed as below, in a declarative form, and can be expressed once. Can be expressed once, and that code that was created can be reused. And so we're looking at second benefit of code reusability. So we can address the various scenarios just by changing the query, just like it is for data. And thirdly, we've seen how we have shown a way to be able to reduce the dependence on stored procedures and be able to have a database optimizer that is able to optimize the entire computation. And over time, as we know, database optimizers improve all the time. So over time, to see that incremental improvement of execution at both range of queries and also the depth of queries. And so thank you very much. If you have any questions, please do reach out. All my details are below. And all of what we've just seen is reproducible. Well, the code is on GitHub and the links are below. So thank you very much.